Alright, so this is going to be the first in a series of videos covering the Maxwell equations, and this is number 1, where we're going to cover Gauss's law. Now, we're going to start with a law that you already know, and that's Coulomb's law. And that says if I want to find the value of the electric field at some point in space, it's equal to some charge, right, over r squared, and I'm going to write it this way, right? You're used to seeing kq over r squared, but let's write out k, right? Because k is its own special number, and it's 1 over 4 pi epsilon naught times q over r squared. R is the distance, right? And now what we're going to do is we're going to regroup some terms, and hopefully you'll notice something that's kind of interesting. First, I'm going to put the q and the epsilon naught together. Epsilon naught's just some special constant of the universe, right? Oh, not equals. Multiplied by 1 over 4 pi r squared. Now if we'll notice, we got this term that contains the amount of charge that we're dealing with, some special constant, and then here we're dividing by the surface area of a sphere. Now why would we want to do that? So if we do epsilon naught equals 4 pi r squared e. Right? That's kind of interesting. It's kind of interesting. And we'll drop the magnitude because we didn't include the direction here. So I'm not telling you which way the electric field is pointing. You tell me it's away from the charge if it's positive, toward the charge if it's negative. We haven't included a vector component here, so we'll just say all we're doing is finding the magnitude of the electric field due to some point charge q. And so this says if we multiply the electric field by the surface area of the sphere, we get q divided by epsilon naught. And for a pictorial representation of what we just did, say I had my charge q right here. I draw this imaginary sphere. I draw this imaginary sphere around it of radius little r. Whose radius is lowercase r. Right? What it says, right? You'll notice here the electric field strength is the same as the electric field strength here, 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 everywhere on the complete surface of this sphere. And it said if we multiply E by the surface area, we'll just call that A, that should equal the amount of charge enclosed inside of it over epsilon naught. Now, of course, we're dealing with a unique scenario where every single bit of this sphere, every point on the sphere, is the same distance from the charge. And there's a better derivation, there's an actual derivation of Gauss's law from Coulomb's law, but we won't get into it. Basically, look at this and we say, you know what if it's always true? Not just in the case where I'm dealing with a sphere. I could have charge in a blob like this, and I'm not even going to pick a sphere. I'm going to pick this, differently shaped blob, right? And even then, right, so now, since the electric field isn't the same everywhere, we can't just assume that we're multiplying by the surface area. I have to multiply the electric field here by the surface there, electric field there by the surface there, so on and so forth. And so the formal way of writing Gauss's law is to say we're taking the surface integral of the electric field over an area, right? And so notice this is a dot product between our electric field vector and a surface component vector. So this is an infinitesimal component of the surface, and we stick a normal vector onto it. So let's say we choose a little bit of the surface, right, that's pointing, say, upward, like that. So this is the normal vector. And so we just want, if the electric field is pointing like this, then it's not really flowing out of the surface in a way. If it's flowing like this, then it's going completely out. And if it's like this, well, there's part of it that's coming out, part of it that isn't coming out. And so how we express the amount of the electric field that's coming out of the surface, or the flux of the electric field through the surface, we just take this dot product right here, and then we integrate over the entire surface. And so we'll run through two examples of Gauss's law. One that I'm sure you've done before, and one that you might not have done before. First one, I'm going to say, let's say we have an infinite plane of charge. So this plane extends infinitely in every direction. Some of my arrows, all right. Extends infinitely in every direction. And I'm going to give it a charge per unit area sigma. So that means if I were to cut a 1 meter by 1 meter section of this plane, so 1 meter, the total amount of charge located on that square would be sigma. So this is a charge per unit area sigma. And what I want is for you to tell me, let's say I choose some height z above the surface of my plane. Find me the electric field strength right there. So, in order to do this, we're going to exploit some symmetries in the problem. Let me draw it better. So we have an infinite plane of charge. Right? And so we're going to exploit two types of symmetries, or two symmetries that are present in this problem. Notice, if I stand right here, right, and I look in this direction, right, I'll see an infinite amount of charge in that direction, an infinite amount of charge behind me, and an infinite amount of charge in every direction I can think of. What if I turn and I look this way instead? Will the plane look any different to me? No, it won't, right? Because it's infinite in every direction. I still have an infinite amount of charge in front, behind, to the left, to the right, everything. So, symmetry number 2. If I'm standing here, right, and I look outward, right, I see an infinite amount of charge on this side, infinite behind me, to the left, to the right. Now if I stand here instead, will I see something different? No, again, infinite amount of charge behind me, in front of me, to the left, to the right. So it doesn't matter where I stand. That means the electric field, let's say here, should be the same here, as long as we're at the same height above the surface. There is no symmetry that immediately tells us that, oh, the electric field is going to be the same regardless of the height. So we can't exclude that yet. So now we're going to use Gauss's law to do this calculation. Now, you realize we could use Coulomb's law. I could pick a point here, and then we could say this is the x-axis, and this is the y-axis, and here's our z-axis, right? We could say, oh, take this point here, right? It's got some infinitesimal amount of charge, and it's this distance away, so maybe it contributes a tiny bit of electric field. We take this point and add up its electric field, take this point, and then we integrate over the entire infinite plane. But that's a pretty difficult integral to take. It's doable, but there's a much, much easier way to do it. And it comes from taking advantage of the symmetries that we just talked about. So let's draw it. So we're going to use this equals Q enclosed. Now, notice that Gauss's law, we are only concerned with the amount of charge located inside our surface. So let's say I had some weird blob of charge, right? it's got a, a total amount of charge Q on it. But if I choose my Gaussian surface to also be some strangely shaped blob, right? The flux through this surface will only be the charge that's actually contained inside of it. I don't care about all this up here. That's not to say they don't influence the electric field at all. They just, when we're talking about Gauss's law, we only are talking about the flux of the electric field through the surface. So we're going to use that. We're going to say, here's my infinite plane of charge. And for my Gaussian surface, I'm going to choose a cylinder. And it intersects the plane right here, and then it comes out of the plane. Maybe I should. Alright. There we go. Right? And, awesome. So notice, we'll say the surface area of this, we can say it's pi r squared, right? But I'll just say we know that it's some number a, the surface of this. And then the amount of charge contained is just going to be right where that cylinder intersects with our surface. So it's just going to be sigma times a. Right? That is equal to Q enclosed. Charge enclosed. Alright, now look at the side face of our cylinder. Let's draw a line like that. You see how for every charge here, it's going to contribute some amount of electric field pointing this way. But I can also find a corresponding charge right there that adds an electric field this way. And so for every single charge, I can actually do this, right? And we can make the electric fields all cancel out so that what's left on this side is only the vertical component of the electric field, because their vertical components don't cancel when you add vectors like this, but the horizontal components do. But wait a second. When we take a surface integral, we're only concerned with the component of the electric field that's perpendicular to our surface. And we've just shown that everywhere on this side face of our cylinder, the electric field is only parallel to it. So we can ignore that portion of the electric field completely. And we only have to care about the electric field up here and down here on the bottom face too. Can't forget about the bottom face. Right? So that means the total amount of electric flux is the electric field here. We'll say it extends the same distance above and below the surface. So even if the electric field does depend on your height above or below the surface, we know it's going to be the same because we've chosen it so that our cylinder extends the same height above as it does below the surface. So the total electric flux through these two faces is going to be E times A, right, times 2. And now all we're going to do is just relate these two expressions. So, because Gauss's law is true, this means that 2EA equals sigma A. Notice, the surface areas cancel out from both sides, and the electric field, at least its magnitude, is equal to over epsilon naught. So remember, it's Q enclosed over epsilon naught. All I've given here is an expression for Q enclosed, so we have to divide this side by epsilon naught, which I forgot to do. But this is just going to be 2 epsilon naught. And that is how we derive the electric field above an infinite cylinder, above an infinite plane of charge. Now, why is this useful, considering we never deal with infinite planes of charge in real life? Well, let's say I just took this section. Now, don't imagine that this plane extends infinitely in every direction. But look at what we took out. This amount of charge its electric field is mostly going to be pointing horizontal to the side. But as we saw, right, this is the part that gets canceled out anyways, right? So it's not even contributing that much to the net electric field above our surface. And this effect only gets stronger as we move further and further away, because the electric field is going to end up pointing like this, 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 this. And as we saw, it's only the vertical component that doesn't get canceled out. Well, there isn't a whole lot of vertical component in this vector. And so when we deal with large plates of charge, it's actually fair to approximate them as infinite planes and realize we're not leaving that much out. We're leaving out a lot of charge, yes, but they contributed so little to the electric field anyways, it doesn't matter if we ignore them. The second example. This one is going to be a bit tougher. I should probably rewrite. Alright, so now for our second example. This one's going to be a bit tougher than the last one. So let's say I have a sphere of charge. Now, the charge is evenly distributed in this sphere, so it's got a uniform charge density, we'll call it rho. Now let's say, first let's draw the axes. Let's say I took this point right here, and it's half the radius away, and then I cut out a sphere like that. I just completely cut this out. Now I want you to find me the electric field at the center right there. So let's show what I mean by that. Basically, I have a sphere, a solid sphere, and I've hollowed out a portion of it. Now I want you to find me the electric field at the center of this hollow portion of our sphere. Right? And we're actually going to use Gauss's law to do this, because this integral, right, if I want to now integrate like this charge and how it contributes, this charge and how it contributes, this charge, how it contributes, this is a terrible, terrible integral. But we're not going to do it that way. We're going to do it with Gauss's law. And with Gauss's law, we're going to combine Gauss's law with another thing, right? Let's say, let's just consider a separate example, right? Let's say I have one charge here and another charge here. And I want to find the electric field at a point here. How would I do it? Well, this is the easiest, this is one of the first things you do when you first learn Coulomb's law, right? Well, the total electric field is just equal to the electric field from the first one plus the electric field from the second one. Right? It's the easiest type of problem associated with this kind of thing. And we're actually going to use this. But we're going to do it with Gauss's law. And this comes from realizing that, go back to before I cut this out. Right. The electric field at this point, right, is, well, it's the electric field due to this charge right here, and 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 all of the charges in our sphere. Or we could divide it up another way. We could think of the electric field here as being due to all of this out here. All of this out here, plus the contributions due to this out here. Right? How does that make things simpler? It looks like I'm just restating the problem. we know, let's call this one, this crescent-shaped thing, we'll call this S1. We'll call this piece that I cut out S2. Now, do you see how our original total sphere is just S1 plus S2? And it's got some electric field. I mean, I don't know which way it's going to point, but I think it might be that way. Alright, it's easy for us to calculate the electric field due to a perfectly symmetrical solid sphere, but it's hard with this. But we're going to take advantage of the fact that the electric field here is just the sum of these two electric fields. So, E of, we'll call this entire thing S3. So the electric field due to all of sphere number 3 is just equal to the electric field due to sphere 1 plus the electric field due to sphere 2. And remember, we're not solving for E3. We're solving for the electric field exerted by this thing after that chunk gets cut out. So what we're really solving for is the electric field due to S1, or E1. E1 is equal to E3 minus E2. Right? So basic algebra. But notice, right, E1 is a very hard thing to calculate all by itself, at least if you're going to do it by taking the integral over this crescent thing. E3 is a solid sphere of charge. E2 is a solid sphere of charge. Calculating electric fields due to solid spheres of charge is incredibly easy. And here's how we're going to do it. So this is S3. We want to calculate the electric field here, right? Well, let's take our Gaussian surface to be this smaller sphere that's inside. Well, that's supposed to be right there on the axis. This distance is going to be R over 4. 3R over 4. Because it was 1/2 the radius, and then we cut it out like that. It's got to be 3R over 4. Alright, well, let's look at Gauss's law. Notice how this is spherically symmetrical. That means the electric field, at least the strength of the electric field here, right, should be the exact same as the strength of the electric field here, or here, or here, or here, and they must point radially. If I stand here and I look toward, let's say I stand right here, inside the sphere, and I look straight at the center, I'll see half a sphere of charge on one side of me, half a sphere of charge on the other side. Let's say I stand here instead, and I look toward the center. I'll see half a sphere of charge to the right, half a sphere of charge to the left. So this is symmetrical in both these situations. What that tells us is the electric field strength must be pointing in the radial direction, either outward or inward, we don't know yet. And it must be the same in strength everywhere along the surface of this sphere. Well, that's perfect for Gauss's law. Because Gauss's law says magnitude of the electric field integrated over the surface, dA, is equal to Q enclosed over epsilon naught. But if the electric field is the same everywhere, and it always points in the radial direction, in other words, it's always perpendicular to our spherical surface, this just becomes E times the surface area of the sphere, which we'll replace with 4 pi r squared. But now we have to be careful with Q enclosed, because it's not rho times 4/3 pi r cubed. Because we're not considering all of the charge in this sphere. We're just considering all of the charge in this smaller one. So that actually equals, so Q enclosed actually equals the charge density times 4/3 pi times 3r over 4 cubed. And then it's easy and we can find the electric field due to it. Oh, we have to do it anyway, so let's carry it through. This is going to end up equaling rho 4/3 pi r cubed times 27 over 64. And then we can divide 64 by 4. We can divide 27 by 3. That becomes rho pi r cubed times 9 over 16. Very nice. So it's rho over epsilon naught pi r cubed times 9 over 16. Alright. So now we just divide both sides by 4 pi r squared. E equals. We have an r squared over here, with an r cubed over there. So we still have a factor of r left. The pi's disappear. 4, so 9 over 16 divided by 4 is rho over epsilon naught times 9 over 64. That is going to be our E3. Right? But you can see how this example, we don't have to do the entire calculation over again for E2. We're just going to substitute, instead of using 3r over 4, we're just going to take r. We'll look at what happens then. This 3 over 4 doesn't even happen. So Q enclosed is rho over the complete r. What am I doing? Q enclosed equals rho times 4/3 pi. Now we have to be careful. Let's remember this. So I'm gonna write that over here. E times 9 over 64. Erase the rest. So that was our E3. Now we're going to calculate E2. E2 was the little sphere, but we looked at its center. Alright? So 4/3, let's start it again. What is Q enclosed in my, right, so I want to pick a Gaussian surface that actually contains my point of interest, where I'm trying to calculate the electric field. But if this point is right at the center, and I'm stubborn and I really want to pick a spherical Gaussian surface, what is the radius of that surface? 0. So Q enclosed equals rho times 4/3 pi 0 cubed. In other words, there is no enclosed charge. But by Gauss's law, that means there is no field. The electric field at the center of a sphere of charge, where the charge is uniformly distributed around the center, is 0. Well, that's awesome. This then means that the answer to our problem, the electric field here, is just equal to E3. Now that's kind of an interesting result, right? Because we calculated E3 by assuming that this hadn't been taken out yet. And when we took it out, the electric field at the center didn't change. And that's because this sphere wasn't contributing to the electric field at that point anyways. It was not contributing at all. And that's easy to see, because this point is going to add some amount like this, but this point is going to add it in the opposite direction. All of these points are canceling each other out. It's another way that we could have gotten to the answer, but this is more interesting and it's more formal at least. And that's it for Gauss's law.